Okay, so this is lecture 22. By the way, I don't think we need any extra lectures or something like that. So we'll just make do with what we have. So today's lecture, we are going to see the first sort of sub-exponential factoring algorithm, which is called Dixon's algorithm. That's what we'll do towards the end. And it's going to be based on this congruence of squares method that I sort of very briefly described last time. Okay, we'll discuss that in more detail. Because almost all modern factoring algorithms seems to follow this template. There's a particular template that it follows, and we're going to try and instantiate the templates with various other techniques. In the process, we'll have to deal with something called smooth numbers. This part, I will just state certain results without proofs. Something like the prime number density theorem sort of a thing. There'll be a similar smooth number density theorem, which I'm just going to state without proof. But hopefully they will be believable enough and we can just proceed with the rest of it, because I really think it's the other ideas in the algorithm which I'm sort of more keen to tell you about, so on. And this particular approach that I'm going to describe, which Dixon's algorithm is a version of, is something called Morrison and Brillhart's approach. And there's a lot of subsequent, minor improvements that kept happening to these approaches, which eventually led to the current best heuristic that we have, which is the general number field scheme. But we will see various steps in the process. And some of these steps will be like, a lot of effort to maybe shave off one constant that is there somewhere. But hopefully I've convinced you that factoring is an important enough problem that, if someone tells you that, today 2048-bit RSA is not secure, it will have reverberations in the world. So many of these times, improving these constants do have big, they have big consequences. Okay, good. So let me just do a recap of the things that we did last time. And though we won't exactly need those things in today's lecture, but often what all factoring algorithms do is like they will try out these simpler algorithms first. If these simpler algorithms already find out a factor, then you don't have to throw these hammers at your problem. So one of the algorithms that we saw was what we saw was the Pollard's row method. And the rough idea was the following. If you keep picking up numbers at random, okay, and let's say your integer n was actually factorizing into p times q, then in the Chinese remainder representation, once you choose about square root t such integers, some two of them will have the same first coordinate. Okay, and this is what we refer to as the birthday paradox. Like if you pick up random samples from a space of p elements, then after about something like square root p samples or a little bit more than that, with high probability there will be some collision. Okay, and these collisions are very good for you because if you take those differences, then that has a 0 in that coordinate, which means that those are numbers that have a non-trivial GCD within. So a natural thing is like, can we somehow efficiently find these collisions? Can you find two numbers that happen to have the same value in one of the coordinates? Okay, so, and this in general was the collision detection problem. And we then looked at a deterministic version of it where I'm not really picking things at random, but I'm pretending to pick things at random. That is, I start off with some x, and my next element is just going to be x squared plus 1 mod n. And I just keep doing this as a sequence. I have x1, x2 is going to be x1 squared plus 1 mod n. That is going to be x2. And x3 is going to be x2 squared plus 1 mod n. So you have a certain sequence. And heuristically, you sort of tell yourself that even under this sequence, the birthday paradox sort of applies. In the sense that this sequence looks random enough that, even after about roughly square root t samples, you should start expecting a collision in the first coordinate. And this is a heuristic, of course. We only know the birthday paradox is true when we are picking things completely at random. Expect some collision after about root t such samples. Now, once you have a deterministic version, it's perfectly suited for this hare and tortoise algorithm that we saw last time. And because then it just feels like you have a loop and you're trying to figure out, can I get a collision somehow? And we combined the two together. We combined this with Floyd's cycle finding algorithm to get an algorithm that runs in time roughly about n to the 1/4. Again, I'm ignoring all sorts of log factors, etc., etc. And the important thing was the space was also very small. So at any step in the algorithm, you only had to remember two numbers, which is where the hare is currently and where the tortoise is currently, and maybe a counter to sort of tell yourself how many steps have I tried this far. Okay, so that was how it was. And I do want to mention, because I forgot the reference last time, is that currently, if you ask, okay, I don't want these heuristics. I want a rigorous running time analysis, and I want a deterministic algorithm with such an analysis. What's the best algorithm? Turns out there is an order n to the 1/5 algorithm due to David Harvey. And this is a fairly recent algorithm for factoring. So in terms of deterministic, rigorous running time algorithms, this is the best. Okay. But in today's class, one of the things we will see is that a rigorous randomized algorithm whose running time will be sub-exponential. And that's what Dixon's algorithm is. So that's what we'll eventually get to by the end of today's lecture. Okay. So let's just proceed with Krajcik's the congruence of squares approach. Okay. Roughly speaking, what this says is the following: you are really looking to find two elements, alpha and beta, such that alpha is not equal to plus minus beta, in the sense that it's a non-trivial pair of elements, such that their squares are identical modulo n. So in some sense, if you think of alpha squared, if this was equal to gamma, then typically there should be two square roots for gamma, which is plus root gamma and minus root gamma. But you basically want to say that no, there are these other weird square roots, like which are not really plus minus of each other at all. Okay, and this happens only when n is a composite number, has at least two prime factors, etc. And we're going to somehow exploit it. The goal is to somehow find these alphas and betas such that alpha squared and beta squared happens to be identical, under the hope that once you find this, you will be able to pull out a factor for this. And how do you pull out a factor? You're just going to use the fact that alpha squared minus beta squared is now going to be 0 mod n. And alpha squared minus beta squared nicely factorizes into alpha minus beta into alpha plus beta. And therefore, the hope is that one of these GCDs is hopefully non-trivial. Okay, that's the idea. So this is what this is the general approach. All the modern algorithms is really a question of how do you do the first part. That's the crux of it. How do you somehow get a sense of how are you going to find these alphas and betas? But before we do that, let's even ask ourselves, why should such alphas and betas even exist? Okay, and again, I'm going to assume that this n equals p times q, that is, it has at least two prime factors, because like we mentioned earlier, if it's a power of a single prime, we are just going to assume those are all things that we have handled so far. Okay, so why is that the case? So let's just pick an arbitrary element alpha in Zn. Okay, under the Chinese remainder representation, okay, this will have some representation of the form x comma y in Zp cross Zq, because we know that these two rings are isomorphic. So therefore, this alpha has some representation as a tuple, something that comes in Zp and something that comes in Zp. Okay, now what's alpha squared going to be? What is its representation going to be? The whole point of the isomorphism is that you can work coordinates. So this is just going to be x squared comma y squared. Okay. Now can you tell me a beta such that beta squared happens to be equal to alpha squared, but beta is neither alpha nor minus alpha?
X comma minus y.
That's right. So you look at this sort of weird cross that you have here, which is x comma minus y. This is some element, and let's assume that x and y are not equal to 0, so that this is truly a new element. Okay, it's not plus alpha, it's not minus alpha either. Okay, so this basically implies that beta squared also has a representation which is basically x squared y squared, which we know is equal to alpha squared. but alpha is not equal to plus minus beta, because at least one of the coordinates will be different. I mean, if it is plus beta, then it differs on the second coordinate. If it's minus beta, then it differs on the first. So again, once again, this was like this Chinese remaindering is basically going to tell you that because there are multiple components, it may be the case that within each component you have only two square roots, the positive, the plus one and the minus one in some sense. Okay, but because there are multiple components, you can do this weird mixing and matching business, and therefore you end up getting a lot more square roots potentially of a certain number. Okay, so that at least is going to tell you that if n were composite, then this Krejcik's approach is that hopefully there are alpha squares and beta squares that will alpha and betas of this type, and therefore we are hoping to find one such thing. Okay.
Just like a small curiosity, is it like are now these the only square roots, like just the plus minus flipping thing?
Yes, in fact they are, because the point is x squared within ZP has only two square roots because this is a field.
Okay, then okay.
Right. So therefore there are only two possible coordinates here. There are only two possible coordinates here.
Yeah.
So you will have four square roots. If it so happens that, I mean, if this and this are both squares inside the corresponding worlds, then there will be four squares.
Right.
Otherwise, there won't be any square. There won't be any square root for those things. Okay, great. So now let's come to this thing of how do we find these congruence of squares? And by the way, this is something that goes back to even as much as Fermat. So he also was, I mean, there were suggestions that were made even by him. And the idea was roughly the following, which is, in some sense, this is like the first thing that you try. So you basically say, let's say that m is basically square root of n, but the ceiling. Okay. So we'll take the ceiling of square root of n. And let's just try out the following. So I'm going to look at m plus 1 the whole square mod n. Okay. Because I know m plus 1 the whole square is already going to exceed n. So when I go mod n, I will now end up with a much smaller number. Okay. And maybe this is a square. If this is a square, then it's so high. For example, if m plus 1 the whole square mod n happens to be 9, then you know for a fact that alpha equals m plus 1 and beta equal to 3 is an example of such a thing. This congruence of squares that you want. Okay, maybe m plus 1 whole square is not a square. Okay, then let's do m plus 2 the whole square mod n. Okay, and keep repeating it until this residue happens to be a square. Okay, it's a rather silly sort of attempt, but nevertheless, it's the first thing that you will want to try. I mean, I'm looking for a square to be something different. So it makes sense to choose a number large enough, square it so that there is some wraparound. And after a wraparound, somehow hope that, whatever remainder that you got happens to be a square as well. Okay. But now let's ask ourselves, if you suppose you say that, when I take m plus 1 the whole square and look at its remainder, it sort of looks like a random number. It's not really random, but again, let's just put some heuristics and say it's some random number in some small enough range. But the number of squares are very few, right? I mean, within the first n numbers, there are only about root n squares. So the chance of this residue being a square is rather minuscule. Okay, but the issue is, there are very few squares. Okay, so that's one reason why this sort of, trying to get a congruence of squares in one shot. Okay, it's a bit too good to be true. I mean, it's very unlikely that, after a few tries, you're somehow going to end up with something where m plus I the whole squared mod n suddenly happens to become like a square itself. Okay, this is perhaps too unreasonable. It's like too good to be true. Okay, And Morrison and Brillhart came up with a different approach to sort of say, no, let's not try to get these squares like at one shot. Let's try to build up to a square slowly. Okay. So what I'm going to do is I'm instead going to just give you an example as to what happens to 1649. I don't know if people recognize what the factors of 1649 are, but okay. But let's just see how Morrison and Brillhart's approach will work. So the first thing is we need to get a sense of, what is this m? Like, what is the rough square root of this number? So that is, okay. So if I take 40 squared, this is 1600. So it's still a little less than that. So let's look at 41 squared. This happens to be 1681. Okay. So our m is 41. Okay. So this is what our m is going to be, because it's the smallest number that is, oh, sorry, m is not 41 squared, m is 41 in this case. Okay. So let's do the following. So let's start with 41 squared, 42 squared, and then slowly build up to. So what is 41 squared mod n? Okay, I'm just going to write down. So this happens to be 32. Okay, now if you look at 42 squared mod n, okay, this happens to be apparently 150. Okay, if I do 43 squared mod n, this happens to be 200. And if I look at 44 squared mod n, and this happens to be 287 or something. Okay. Now, on the face of it, it feels like I'm not making progress at all. I mean, none of these are squares. Okay. I mean, like it just feels like we are doing Fermat's thing. But if you notice something, maybe you notice that if I actually multiply 32 with 200, I get 6400, which happens to be a square. Okay, so what I'm saying is that this basically implies that 41 squared into 43 squared equals, modulo n, like 32 into 200, which is 6400, which happens to be 80 squared. Okay, so therefore, let's try the following. So let's try GCD of 1649 with, you either do the sum or my alpha in this case equals 41 into 43, and beta in this case is equal to 8. Okay, if you do GCD of this with alpha plus beta, you end up getting 97. If you do GCD of 1649 with alpha minus beta, you end up getting 70. Okay, and 1649 happens to be equal to 97 times 17 or something. I think, or at least you just got two factors. Okay, so something we have made some progress here. But how are we suddenly supposed to discover that 32 times 200 is now suddenly a square? How could we have discovered something like that? So to make life simple, what we'll do is we'll try to factorize the sort of numbers we end up getting. Okay, hopefully these numbers are small enough such that factorization is a little easier or something, but we'll try to formalize this soon. So I know 32 equals 2 power 5. So 115, I can divide this by 5. I think I end up getting 23 or something. And I'm going to pretend as if I don't even know if 23 is a square or not or whatever. It's not useful. The only primes I know is, let's say, 2, 3, and 5. Like anything beyond that, I don't know how to divide things. Okay, I'm just going to tell myself I'm not even going to attempt to divide by larger numbers because I don't know the multiplication tables well enough or something. So 200, fortunately, this is going to become, what is 200 going to be? So it is 2 cubed. So it's 8 into what? What the hell is the factorization of 200? I should know this. So this is 10 squared, which is like 5 squared into 2 squared into 2. So, right. So this is going to be 2 cubed into 5 squared. Okay. And now it's maybe easier to notice that this times this will end up being a perfect square, because when I multiply this with this, the exponent of 2 suddenly becomes an even number. The exponent of 5 also becomes an even number. And therefore, I know that, if once all the prime exponents are going to be even numbers, then I know it's a square. Okay. So that's going to be the goal. So the goal is actually going to be, we want to build a lot of these small congruences. Okay. And try and somehow find a product of them that happens to be a square on both sides. It will always be a square on the left-hand side because everything is a square on the left-hand side. But what we want is the product of somehow these things, whatever subset that you choose happens to be a square on the right-hand side. So is the overall idea clear as to what we are trying to do here? I mean, okay, we still need to formalize a lot of things, but at least we seem to be doing something better than what what the Fermat attempt was, which was to just keep trying until one of these happens to be a square. And this is basically saying that it's too much to ask for one of them to be a square in itself. But let's combine a few of them and create a square on our own. Okay, good. So now in general, this is the Brillhart and Morrison-Brillhart approach. It says the following: start with the smallest point where some sort of wraparounds happen. And from that point onward, start your search. Okay, you look at A1, which happens to be m plus 1 the whole square. Okay, but you look at it mod n, so it becomes some y1, which is a much smaller number. And A2, you try the same thing for A2, and this becomes y2, blah, blah, blah. You try something like R things. Okay, and what you do is you try to factorize y1, y2 till yr. Okay, so that is, let's say this looks like p1 to the e11 till pk to the e1k. Okay, and this looks like p1 to the er1 all the way till pk to the erp. That's the factorization of just y1s. y1 is equal to this factorization, y2 is equal to this, and yr is equal to this. Okay, and now what we are going to do is find a suitable subset of these whatever r numbers, such that this product of yi, where I comes from the subset T, is a square. Okay, which is equivalent to saying that is for all j, where j is basically, I'm thinking of as the exponent corresponding to pj. Okay, and this is just saying that summation over all I subset of t of eij is even. Right? We are just basically think of them as just these exponent vectors. I mean, forget the actual basis, etc. You're trying to find a combination such that all the coordinates now become even numbers. Once you know they're all even, once you know that is a perfect square. Okay, so how are we going to do this? So we're just going to write down all the exponent vectors. This is the exponent vector for y1, this is the exponent vector for y2, and this is the exponent vector for yr. Okay, and we are hoping for something where all of some sum of these things such that all of them happens to be an even number. Now, how would you, I mean, if I give you these vectors e1, e2 till er, how do you find such a combination? So I'll give you one additional thing. Suppose this r was bigger than k. That is, there are more rows than the number of coordinates. Okay, let me ask you a simpler thing. Can you find a linear combination of them that gives me all zeros? If I had asked you that, what would you have done? Like these are some vectors. And I'm asking, can you give me a combination of these vectors that happen to add to 0?
Like determinant.
I mean, you'll do some linear algebra, right? Like this Gaussian elimination and try to find the kernel. We have to do exactly the same thing, except now you want all of them to be even. Can you go to a world where this is saying that I want their sum to be 0? Okay, so this is just saying you do linear algebra, sorry. Over F2. That is, just put a 1 if that was an odd number and 0 if it was an even number. And now just think of this as you've given a bunch of vectors over F2. And I've given you more vectors than its dimension. That is, I'm telling you that R is bigger than K. So there must be some linear combination of them which should add up to the all zeros vector. Okay, and you find that. And this is just, you're doing Gaussian elimination, etc. So this is just, this is Gaussian elimination. Okay, so that's the idea. So once you manage to factorize y1, y2 till yr, by looking at these exponent vectors, you can always find out a suitable linear combination of them. Okay, so now here is a question. We started off with the task of factoring n. And now apparently as a subtask, we need to factor these y's. Now, how the hell are we going to do that? I mean, is this some weird recursive algorithm where we are going to try this or something? And the cool idea here is that it's just, you just factorize what you can. And we're going to use the fact that some of these numbers were rather easy to factorize, just because of the fact that all its prime factors were very small. Okay, 32, I mean, I just need to divide by 2. I need to know the 2 tables, I can do 32. For 200, it seems like, okay, I need to know 2, 3, and 5 tables, and then I can do that. 115 and 287, I could maybe give up and say that, okay, I don't know 23, I have no clue if it's a prime or not, I'm going to give up on that or whatever. So we can basically just do the same approach that Fermat did. Keep enumerating these, m plus 1, m plus 2 the whole square, m plus 3 the whole square. Try to factorize the things that you get on the right hand side. If you manage to succeed, great. You found a suitable exponent vector, etc. If you don't manage to succeed, just throw that away, go to the next one. And hope that sooner or later there will be one of these easy factorizing things, and you can work with those instead. Like, we don't need to be completely stuck up on the fact that each of these yi's I should somehow factorize. So, like, we'll just do what we can, and if we can't, we'll just proceed to the next recipe. Okay, and this entire discussion, to make it formal, leads to what are called smooth numbers. Okay, because we are basically going to tell ourselves that I have a particular bound p. I am willing to factorize numbers as long as its prime factors are less than p. Anything beyond that is too hard for me, I'm going to give up. Okay, so we'll want to know what are these integers, all of whose prime factors are within this bound p. And they are called b smooth numbers. Okay, or there are multiple ways of saying it, which is that these are all integers of the form p1 to the e1, pk to the ek, where p1 to pk are the primes less than p. So all numbers that are only products of these primes. Okay, things that involve prime factors bigger than b, I don't care, and I'm not interested in that set at all. And one of the notations, which is s of n comma b, it just refers to among the first n numbers, what are all the b smooth numbers. Okay, so going back to what we were doing earlier, we are going to set ourselves a bound b. And for all the yi's, which were these residues that we got, if they happen to be b smooth, we will factorize them. Because that part appears like, I know my primes are small enough, so I can try out various things, etc. In fact, if it so turns out that, just dividing by these primes are not enough to factorize this number, you just throw that away. That's not a smooth number, and just move on to the next one. And you're just going to hope that there's hopefully enough smooth numbers that eventually what I want is a certain number of these congruences to do this linear algebra part. So yeah, so we'll just look for that many smooth numbers in the hope that one of them works out and so. Okay, so this is what a smooth number is. So let's first ask the following question. Suppose I promise to you that I give you an integer m that happens to be b smooth. I give you this promise. How much time will it take for you to factor this number in?
I mean, it will be some like, yes, will poly B.
Yeah, in fact, let's be a bit more precise about that. Because this b, which poly it is, will start playing a role in the running time analysis. So I want to know, when we say poly b, is it b squared, b cubed, is it d? So what would the algorithm be? What would the stupidest algorithm be?
Keep dividing by things at most.
Right. So let's first do one thing. Let's just run over all the first b numbers and pull out all the primes. Okay, this is going to take about b time, because there's a for loop of roughly length b, and primality test, we know we can do it in polynomial time, so that's like log b, which we don't care about. Okay, so roughly speaking, it's going to take about like O tilde of b time, finding all the primes. Now for each such prime, I need to keep on dividing by that prime and figure out what is the largest power of this number that divides this. Okay, so that's again going to be another poly in log b sort of time, or log b comma log n. So I'm just going to, this is something I'll let you, okay, just find all primes less than or equal to b, and this will take O tilde b time. Okay, and divide. And each of these divisions will take something like O tilde of log b comma log n. Right? Because division, etc., those are all very efficient algorithms. So overall, the total time is going to be like, so the total, I mean, if you're ignoring log factors, it's basically O tilde of b. I mean, it's mostly dominated by the fact that I need to potentially divide by something like b many primes, or something like b by log b many primes. And it's that loop that is actually going to take the most amount of time. Okay, so we're basically going to tell ourselves that for any b smooth number, factoring that number only takes order b time, like O tilde of b time, if you're ignoring log. Okay. Okay, good. So now here is the congruence of squares template. It's usually made up of 3 steps. Okay, so there is an initial part which is just setup of parameters. You need to figure out what is this threshold of smoothness that you want to use. Okay, and then you just need to find the first b primes. This is this initial step that you do. Okay, and we're just going to find the set of b primes, and let's say there are r of them. Okay, and next is this data collection step. That is, you're trying to collect a lot of these, smooth congruences. By that, what you mean is you're trying to collect enough congruences of the form ai squared equals yi mod n, where this ai is large enough. That is like, there is some wraparound that is happening, and so on. And this yi happens to be b smooth. Okay, so you're going to collect, because I need r plus 1 of them to eventually solve that system of linear equations and get a non-trivial solution. Right? I mean, because we are going to eventually then write down this matrix and look for a suitable row combination that sums to 0. So to ensure that there is always a solution for that, we will make sure we have more congruences than whatever the number of columns in this matrix. Okay, so that there is always some row combination that fits. So the data collection step is going to be to find these small congruences where these yi's happen to be smooth. And so that's going to be the data collection step. And then there is the building the congruence of squares. Now you factor each of these yi's, because now you're promised that these yi's were b smooth. Okay, you try and factor these yi's. So you will get a bunch of these exponent vectors. And now you do some Gaussian elimination on this matrix to find a suitable combination T, such that it sums to 0 over S. Okay, And then your alpha is easy, which is just the product of these AIs. This is the left-hand side of this thing. Your beta is going to be the product of the yi's, but the square root of them. And the square root exists because when I take the product of these yi's, all of these exponents happens to be even numbers. So dividing by 2 makes sense. So now you get a suitable congruence of squares, and then you just hope that one of these two GCDs will be non-trivial. If it is non-trivial, you return it. I mean, if it doesn't work, you just try again. I mean, like, okay, so this is what we are going to do. So is the template of the algorithm clear? Is there any part of this that is a little unclear? Because we're now going to go into analyzing what should the smoothness be, and etc. etc. Okay. So this is the general Morrison and Brillhart approach to build a congruence of squares by using the smoothness property. Okay, so there's a very small difference between exactly the Morrison and Brillhart algorithm and Dixon's algorithm, which is just towards how do you find, I mean, what are these AIs? What do you choose as your AI? So in Morrison and Brillhart's approach, AI happens to be the square root of n plus I. You start from there and start looking at squares. So A1 looks like square root of n plus 1 the whole square, then square root of n plus 2 the whole square, etc. etc. Dixon's approach is in fact saying that why are we even trying to be smart here? Let's just pick an AI at random. We just each AI is going to be, we're just going to pick up a random AI, square it, look at its residue, and then try to see if that's a smooth number, etc. Okay, so in some sense, this is conceptually easier, but perhaps a little slower. But I mean, somehow conceptually, it just seems like the most natural thing to try. So far, so good. Okay. Now, as you can imagine, a lot of this algorithm is going to rely on how frequent are these smooth numbers. Because if you want to say that, I'm going to try and find these residues. If it is smooth, I will try and factor it. Otherwise, I'll have to go to the next one. And if I have to keep doing this again and again, somehow at some point in the analysis, it should somehow show up is that what are the chances that when I get one of these yi's, which were these residues, what are the chances that this yi is a smooth number? Okay. And it might, I mean, and so it seems like something that we would want to know is like, okay, if I just look at the first n numbers, how many of them are B smooth? Okay, there should be some density sort of argument that to get a sense of, in order to find r plus 1 congruences, how many should I actually try? I eventually want r plus 1 instances where the yi happens to be smooth. But there will be lots that I will try out and realize, oh damn, this one is not smooth, this one is not smooth, etc. So I need to get a sense of how many yi's, how many such tries should I have until I find enough smooth examples. Okay. So that leads to the following question, which is like, how common are these smooth numbers? Okay. Thankfully, there is a result by Canfield, Erdős, and Pomerantz that gives some estimate. Okay, where if u is some integer, it doesn't have to be an integer or whatever. I mean, like if u is some parameter such that this n and b are related in the following manner. Okay, then the number of b smooth numbers is some weird expression of this. Okay, you don't need to know this expression, but as you can imagine, these sort of expressions will start showing up in this running time analysis, and it's going to be a pain to try and optimize what is the best choice of smoothness, etc. we are going to get. Okay, and in order to assist with all of this, the people who worked on factoring had the insight to come up with this notation, because it really simplifies the arithmetic that you will have to do in the analysis of this algorithm. So whenever there are smooth numbers involved, these sort of what are called L functions will start showing up. And it's a super, super useful thing to know what this L function is, because then these expressions become very neat. It then just becomes you are going to manipulate these two parameters R and alpha and figure out what is the best choice of R, best choice of alpha. So let me just say what the L function is. It's just a notation So L of r comma alpha just refers to the following function, which is alpha times log n power r log n power 1 minus r. Okay, it's just some notation to get used to stuff. I will soon say why this notation is very convenient. Okay, so just to get a sense of things, let's just do some, get our hands a little dirty. What is L1 comma 1? By the way, maybe I should just mention, you can choose this exponent to be e power whatever is the argument, in which case the logs are expected to be natural logs. Or you can choose this exponent to be 2 power whatever the argument is, in which case these logs are logs to the base 2. I'm going to ignore small order terms, so therefore there's no real difference between them. You choose whatever you're more convenient. Okay, so now let's ask ourselves, what is ln of 1 comma 1? That's going to be exponential of 1 times log n. And therefore, this is just n. Okay, what is ln of 0 comma 1?
Just 1.
Not quite. I mean, this is 1, but then this is 0 and this is 1.
Oh, sorry, alpha comes after. Okay.
Yeah, okay, so it's r and then alpha. So therefore, you're going to end up with exponential in log n, which is the same thing as log n. Okay, now suppose you wanted to write n to the u. This is, how would you write this as an ln function?
Alpha should be u and r should be 1.
R should be 1. Yes.
Alpha should be u.
Oh, sorry. Alpha.
Switching.
Yeah, even I keep switching. 1 and alpha. Sorry, alpha is u. I don't know why I keep writing. Okay. And ln of half comma 1 is this thing which is exponential in 1 times square root of log n log n. Okay, so this will be important because this will be the final running time of the algorithm that we are trying to get to. But yeah, so this is what this sort of L function is. Why the hell do you care about these L functions? And the reason for that is this, just basically taking the above whatever CEP bound and just writing both n and m, sorry, the range of the numbers and the smoothness parameter in terms of these L functions, then this probability also becomes in terms of this L function. It's just very convenient that way. It just says that if you're going to pick up an integer in this range, that is among the first ln of r comma alpha many numbers, you want to know how many of them are this smooth. Okay, that nicely becomes another ln sort of quantity. Okay, it really cleans up a lot of the analysis that is going to happen shortly. Okay, this lemma just take for granted. If you want, you can try plugging in these expressions into this and convince yourself that what you get here is basically what this is saying. But for now, just take it for granted that this ln is just a very convenient notation, because when you're dealing with numbers within a certain range that happens to be this smooth, if the range and the smoothness parameter are in terms of these L functions, then the probability is also a similar L function. So it just becomes easier to optimize, saying, what should this parameter be, etc., etc. Okay, so if you want, I will leave this as an exercise. You can try and plug this in and see what you end up getting. Okay, because if you want to know how many of the numbers in the first n things are root and smooth, what should the answer be, by the way? Even without knowing these smooth bounds, etc.
1.
Right. Every number here should be root and smooth. Right? Because obviously all the prime factors of this has to be like I mean, there's every non-prime number. No, that's not quite true, right? I mean, we want all the primes to be smaller than root n smooth. But as you can imagine, almost all numbers will be root n smooth. There are a few numbers where one of these prime factors is very large, but then it has very few multiples. Okay, intuitively speaking, that's the thing about it. So most numbers have to be smooth. You can plug it in because you can write this as ln of 1, 1 and write this as ln of 1, half, and then plug it into this expression and see what you get. Okay, so it gives you a way of getting an estimate of this, which otherwise seems like it's like a difficult thing to try and get a sense of how many of them are smooth. Maybe you know it's not root n, maybe you want to try into the 1/4, into the 1/10, etc. And it will be particularly useful when the smoothness parameter is way smaller than what n is. And when you want to get a sense of how many of the numbers from 1 through n are smooth, writing b in terms of these L functions will start becoming very, very useful. Okay, so before we get into the analysis, etc., let's do some stupid arithmetic with these L functions. Okay, so suppose I have one expression that looks like LR, alpha times LS, beta. What should its product be? In terms of, again, L functions. So what is this? This is exponential in alpha log n to the r log n to the 1 minus r. That's what this guy is. This is going to be the same thing, which is like beta log n to the s log n to the 1 minus s. Okay, so let's do two cases. So suppose it happens that r is smaller than s. Okay, then among these two terms, it's going to basically be dominated by this quantity. Okay, so in this case, this is just going to be L of s comma beta. Technically speaking, I should probably put a beta plus a little o of 1 or something, but I'm being a little sloppy here. And similarly, if r was bigger than s, then it will basically become L of r comma alpha. Okay, what happens when r is equal to s?
The r or s term stays the same when you get alpha plus beta.
Do you get alpha plus beta? So suppose this alpha was equal to, suppose let's say this alpha was half and this was 1/3. So it's exponential of half times something times exponential in 1/3 times something.
So, I mean, the exponents add up.
Yeah. So it's going to be. Sorry. No, you're absolutely right. Yeah. So this is just going to be L of r comma alpha plus beta. Sorry, I was confusing the second thing.
Yeah, there it will.
Okay. So what is if I add these two L functions? I mean, obviously, if r was smaller than s, etc., then it will be dominated by the larger term. So it doesn't matter. So the interesting case is when the first coordinate matches. I have LR alpha and LR beta. What is this going to be?
This will be like the dominant term.
Right. So this will actually be the max of alpha and beta. Okay. Great. So now we are perfectly suited to start analyzing Dixon's algorithm. And Dixon's algorithm, let us remind ourselves what it is. It was basically this template where these AIs are chosen at random. You just choose these AIs at random until, and you're going to do sufficiently many times until these YIs become B smooth. And the rest of it is going to proceed like we were talking. Okay. So there is a prime collection phase, there is a data collection phase, and there is a building of the congruences phase. Okay, so let's do the analysis and get a sense of what it is. We have to choose the smoothness parameter B, and for the moment we leave it floating. We'll say the smoothness parameter is going to be some L of s comma beta. S and beta will figure out soon enough. Okay, so we want to do two things. Find primes less than or equal to B plus data collection plus build the congruence of squares. Okay, let's do each of them. How much time will it take to look at the first B numbers and figure out which of them are primes?
You said this, right? Or O tilde
Yeah, this
of
is just like O tilde of B. Okay. And now let's ask ourselves, how much time will the data collection take? Okay. So the first thing we need to figure out is how many such congruences do we need? So if I'm looking at the first B numbers, the number of the primes that you will find is about B by log B. But let's just say it's B minus 1 or something. I mean, I'm just being sloppy here. So which means you roughly need about B congruences of this type. Because the number of columns in this matrix is like roughly B by log B. So I need to build at least that many rows in order to solve this thing. So we are all talking in the order of B. So I need B congruences. That's what I'm looking for. So therefore, let's just say this is equal to B congruences into number of samples per congruence, sorry, per smooth, or rather per smoothness, per smooth number, times we need to check if each of them are smooth or not. So for each yi, I'll have to test whether it is smooth or not. And very likely a lot of them will not be smooth. So even to get a single smooth congruence, I might have to try out many samples. Okay. And eventually I need B samples. So I need B into number of samples per smooth congruence times the smoothness test I need, the running time of checking whether a number is smooth or not. Okay. And finally, how much time does it take to build this congruence of squares once you find all of these relations? Now that is given by just this, right? I mean, we have this matrix. It's roughly a B cross B sort of matrix. I mean, there are some logs involved, but I'm ignoring all of them. So how much time would it take to do Gaussian elimination on a B cross B matrix? So like if you don't do anything fancy, it's about B cube time. Right? I mean, it's like an n cube operation to do Gaussian elimination, etc. So overall, this part is going to be like order B cube. Is this okay so far? Okay, great. So now let's just put things together. So what is O tilde of B? This is going to be L of S comma beta, which we have not yet decided. Again, I'm dropping all of this lower order terms. Okay, plus I have L of S comma beta. This is coming from B. Now the next thing is I want to know how many samples do I need per smoothness. Okay. Now if AIs are chosen at random, the residues you get are also going to be like randomly distributed between 1 through n. I mean, you're going to get all sorts of residues that are going around. And you want to know what is the probability that among those numbers from 1 through n, that the number is B smooth. Because the expected number of samples you need in order to get a B smooth number is the inverse of this probability. Right? And if you work out exactly what this is, this is basically going to be L of 1 minus S times, with the parameter being 1 minus S over beta. Because it was R minus S into minus of alpha by beta. Alpha was equal to 1 because I'm looking at the range of 1 through n. And there was a minus because it was a probability. I'm doing an inverse, so that minus goes away. Okay. And then finally, how much time does it take to check if a number is smooth or not? This is the same thing as saying you have a number m You're going to continue dividing by all the primes you have until now and see if it completely this thing. And this we already argued that it's going to take about b time. Okay, so that is going to be L of S comma beta. Okay, plus b cube is nothing but L of S comma 3 beta. So far so good? Okay, great. So now let's try. Now that we have this expression, actually optimizing this is actually quite easy. What should you choose S to be in order to make this as small as possible? In fact, notice it's completely dominated by whatever this thing is. So if S was anything other than half, one of these two quantities will give you something which is like L something more than half. So that seems like a bad choice. You're going to lose out on that. So it makes sense to choose S to be equal to half. Okay. Once you choose S to be equal to half, what are you going to get? Okay. So you're going to get L of half comma beta plus L of half comma beta. There's another half comma beta. So I'm going to write it as half comma 2 beta times L of half comma, what do you get here?
Get the part. Why did you choose half?
Because if I don't choose half, so let's say I choose S to be 1/4 or something. Then one of these two quantities will be like L of 3/4. So the exponent of log n will be much, much larger than what you're hoping for. I'm trying to say that the exponent of root log n and the exponent is good enough. So you're just trying to minimize the product of these three things. And the best thing to do is to choose S equal to half at least, so that all of them are dealing with just L half. Did that make sense?
Okay.
Yeah. So now once that we choose S equal to half, we are going to try and optimize on what beta is. So if S is half, what is this going to be? This is going to be 1/2 beta.
But also it depends on beta, right?
I mean, think of beta as just a small constant. I mean, like in terms of the L function, the far more important thing is what happens to this exponent. I mean, this constant is usually the smaller of your concern. Like if you're going to, instead of root log n, if you end up getting log n to the 3/4, I mean, setting a slightly different constant here is not going to help you. Did that make sense? Yeah. Okay. So this is what we have, and then this is going to be L of S comma 3 beta. So if you do all the arithmetic that we had done here, this is going to become L of half comma max of these two quantities. 2 beta plus 1/2 beta and 3 beta. Okay. Now what should you choose beta as? What's the best choice for beta? Now notice that this max of 3 beta is like, okay, actually here it's maybe okay. So if I'll just tell you what the best beta that works is, like if you choose beta to be equal to half, okay, then you end up getting L of half comma, I think you get 3/2 probably. No, you get 2. Okay, because 2 into half will give you a 1. And this will give you a 2/2, which is another 1. So you end up getting. So therefore, the running time equals exponential into square root of log n log log. Okay, was this okay? So this L function really simplifies these analysis because you can just focus on just 2 parameters. And something I want to point out is that there is no heuristic here. Okay, that is, if you choose these AIs completely at random, then all you need to make this rigorous was a proper density estimate of how many of these numbers are smooth. And there you can just use the CEP bound that we had, and then the rest of it just works. So technically it's not 2, but it's 2 plus little o of 1 or something. But I'm ignoring all of these lower order terms. Okay, so this was a big breakthrough because, as we mentioned last time, notice that this is smaller than n to the epsilon for every constant epsilon. So in some sense, it's like a sub-exponential algorithm. It's faster than n to the epsilon for every epsilon that you have. And it's actually not that inefficient. So for instance, so what used to happen earlier was that there was these sort of contests that people had to try and factorize larger and larger numbers. There are these Fermat numbers, which are numbers of the form 2 to the k plus 1. And there was a lot of different people, different groups trying to come up with better and better factorization algorithms and so on. So this was one of the big successes of Krajcik's method. And I mean, this eventually giving like a proper algorithm that factors numbers much faster than the standard trial division sort of approaches. Okay, so before I start going into extra bells and whistles that we can add, I just want to make sure that people understand this particular algorithm completely. It's a very clean sort of algorithm. So I'll just go over the steps just once more. So what we do is we just set a suitable smoothness threshold P. Okay, and we are basically going to tell us that whenever we are trying to try and factorize things ourselves, I am not going to consider prime factors more than P. Okay, so this is the threshold that we have. And the first thing we do is collect all the primes, and let's say there is R of them. And typically you expect this R to be something like B by log B because of the density of prime numbers in the first B things and so on. But I'm just going to hand wave and say, okay, there are roughly about B of them. Okay, and then the goal is going to be to try and find roughly B many congruences of the form AI squared equals yi, where the yi's happen to be B smooth. And how are we going to do this? Well, we just try out different AIs, compute the yi, try and do this factorization using just the primes within the first B things. If it works, then we know it's B smooth. So it's like, great, we found one congruence. Otherwise, we just move on to the next one. We just keep trying it again and again until we have enough smooth congruences. And once we have enough smooth congruences, we just look at their exponent vectors. Just think of this as a matrix modulo 2, like you're working over the field F2, and just do Gaussian elimination to try and get the best, get some suitable row combination that sums to 0 over F2. And that is going to give us a congruence because on the left-hand side, it's clearly a square because I'm taking a product of all of these AI squares. But on the right-hand side, they also happen to be a square because all the exponents are now even. And therefore, you naturally have the congruence of squares given by alpha, which is a product of AIs, and beta, which is the square root of the product of YIs. And this square root actually exists because the exponents were all even. And once you get this, you just do the standard GCD and hope that one of them gives us a non-trivial factor. Okay, and it's just that the analysis is very convenient once you have these L functions, and optimizing it sort of becomes clear that S should be half, and then it's a question of what is the right beta. Okay, so in the next about maybe 10-15 minutes or something, I'm going to tell you about all the effort that went into changing this number 2 to 1. Okay, so the algorithm we will see in the next lecture, which is what is called the quadratic sieve algorithm. Okay, the quadratic sieve algorithm is basically going to be the same running time except this 2 is replaced by a 1. Okay, and it's really like taking apart this template, focusing on each step of this thing and trying to see, okay, can I speed this up? Can I speed this up? And so on. Trying to get any sort of advantage that you can get of the previous algorithms. Okay, and all of these ideas that went into it are quite cool, which is why I want to tell you. In terms of actual complexity analysis, it doesn't seem that impressive. But it did make a big difference between sort of who won the contest in this factoring large numbers thing. Okay, so I'm going to tell you a couple of ways to improve the constants, and both of them are fairly fairly easy ways of trying to improve the constants. But then there is a really cool idea that shows up in quadratic sieve, and that we will defer to the next lecture. So I'm now going to tell you two of the simpler ways of improving these constants. So the first step is I want to revisit this building the congruence of squares. Okay, because this in some sense is just easier to say that, okay, this work was already done by other people, we're just going to use that. Okay, let's focus on what exactly happened here. People gave us a bunch of these exponent vectors, okay, which was the factorization patterns of each of the yi's that were obtained so far. And the goal was to find a suitable row operation of these things that sum to 0. And what did we say we will do? We said we will do Gaussian elimination, which is an n cube time algorithm, or which is an r cube time algorithm roughly. But let's ask ourselves, do we really need to run r cube time? I mean, is the problem somehow a little simpler than a general problem of I give you a matrix and I ask you to find a suitable kernel element or something? What are some special properties that this matrix has, which we can somehow try to exploit? Okay, and here is one observation, which is each row has at most log n non-zero entries. Because what does a row correspond to? It's the different prime numbers that divide that corresponding yi with an odd exponent. How many different prime factors can a number have? This is not some number between 1 through n. So it can have at most log n distinct prime factors. Right? So even though this matrix has r columns, and r is like something like L1/2 or something like that, every row actually has very few non-zero entries. There are only about log n non-zero entries in each row. So in some sense, this matrix is a very sparse matrix. It has roughly b squared many entries, but among them only b times log n many entries are non-zero. The rest of them are all 0. So you could ask, for such sparse matrices, are there better linear algebra algorithms? And this is a whole field of study. Okay, there's this whole Langchos method and Biedermann method, etc., etc. And this entire field of study is about trying to do linear algebra for sparse matrices. Okay, and turns out that there is an algorithm which runs in time m times w. If you have an m cross m matrix and you want to, let's say, find its kernel or something, but you're promised that there are only w entries overall. Sorry, w non-zero entries overall. Okay, in our case, what is m and w? M is equal to b roughly, because that's the dimensions of the matrix that we are looking at. And what is w going to be? Well, each row has at most log n entries. So therefore, w is going to be something like b log n. So what happens is, instead of the order b cube time that we had, we can now have an order b squared time algorithm to find this congruence of squares a little efficiently. Okay, so let's just take this for granted and let's just plug it into the algorithm that we had earlier. So if you revisit the analysis, instead of the 3 beta that we had, it's now going to become 2 beta. But unfortunately, this still doesn't help, because if you try to optimize this also, you get beta equal to half. And you end up with 2. I mean, this still is going to be L of half comma 2. Okay, so we try to throw one cool trick on this problem in the hope that you come up with a better factorization algorithm, but unfortunately, the dominant step appears to be elsewhere. So we still haven't really made progress in getting the algorithm to be a little faster. Okay, any questions with this part? I mean, I'm saying this because it does. I mean, like the fact that it doesn't help yet is important, because as we make more and more improvements, suddenly these things will at some. I mean, right now this thing is too large that reducing this did not help. But once we figure out a way to reduce this, suddenly changing this 3 beta to a 2 beta will start becoming relevant. Okay. So now let me tell you the next trick that was done in order to improve it, which is to try and make the numbers small. Currently, what can I say about the yi's that I end up with? I picked up a random AI, I squared it, I got its residue modulo n. And it feels like I can't say much beyond the fact that, okay, the yi is some number between 1 through n. Okay. And let's ask ourselves, is there a way in which we can make these yi's quite small? Okay. And this goes back to the Morrison-Brillhart's original approach, which is to say, suppose my AI was equal to the square root of n, the ceiling plus I, the whole squared minus n, or this used to be this mod n, but let me just say that this is equal to this minus n. Okay. Now imagine the situation where I is very small, like it's much smaller than n. How large is this number going to be? Okay, so this is basically going to be actually square root n plus maybe a delta in order to make sure that this is the whatever the floor, or sorry, the ceiling of square root n. Okay, plus I the whole square. Okay, sorry, minus n. So this is just going to be n plus 2 square root n into delta plus I plus delta plus I the whole square minus n. Okay, so the n sort of cancels off. And I'm thinking of I as being way smaller. So delta plus I the whole square is also much smaller. So it's really dominated by just this term. Okay, so the point I'm trying to make is that this is equal to order square root n if I is small. Okay, now sorry, this is not my AI, this was my yi. I mean, because AI was the square root n plus I the whole square, but the residue is this yi. Okay, and we were somehow hoping that the yi's are the ones we want to be smooth. And naturally, if yi's are in a smaller range, or rather they're quite a small number, the chances of it being smooth also increases by a little bit. Okay, and here is where we are now going to make this big heuristic, which is that y1, if you look at y1 through y whatever, I don't know how many such numbers you're going to consider as the same density of p smooth numbers as something in, let's say, 1 through n. I mean, the CEP bound was basically saying that if you look at the first n numbers, it tells you how many of those numbers are expected to be smooth. But I'm going to somehow like wave my hands and basically say, I have a certain set of R numbers. But I'm just going to make this heuristic assumption that even among the set of R numbers, you roughly expect the same amount of density of smooth numbers. Okay, this is perhaps a little unjustified, but I just want to say that, I'm going to say this is some set of R numbers within 1 through root n, because we are basically saying that all of these numbers are like within about root n or something. And then I'm just going to wave my hands and basically say that, yeah, roughly the number of smooth numbers is basically going to be the density of smoothness within 1 through root n. Okay, so therefore, the probability that a random, sorry, when I pick I want to know how many, in order to get one smooth relation, how many do I need to end up get? What am I saying? So basically what I want to say is the following, that is, I want to know, we were trying to look for these smooth congruences. How many different samples do we need? Okay, so the number of samples per smooth congruence this is going to equal the reciprocal of the probability that a number within this range is smooth. Right? So this is the reciprocal of the probability that a number less than or equal to order root n is B smooth. Okay, and let's be a bit more precise. What do we mean by less than or equal to order root n? This is L of 1 comma half. Okay, and this B was L of, I don't know, S comma beta or half comma beta. Okay, so therefore this probability ends up becoming L of half comma minus 1 by, or the number of samples turns out to be this divided by 1 by 4 beta. Just because of the fact that there is this extra half that is here, and that half will tag along in this sample complexity. Okay, so that's what this becomes. So plugging this in, so what do we end up getting? We end up getting something like L of half comma max of 2 beta plus 1 by 4 beta as opposed to 1 by 2 beta last time, comma, now throwing in this Lanchos, Wiedermann sort of stuff, etc. This is a 2 beta. Okay, and now this is maximized, or rather this is minimized at, I think, beta equal to 1 by 2 root 2. Okay, I mean, notice that this will always be larger than this because it's like 2 beta plus something. So this is sort of irrelevant. But the fact that it is not 3 beta and it's 2 beta, now it starts playing an important role. But now it's a question of, okay, what do I need to choose beta so that this becomes as small as possible? So it makes sense to somehow make like 2 beta and 1 by 4 beta equal, which basically means beta should be like 1 by root 8. And that's why you get 1 by 2 root 2, which gives rise to an algorithm which is exponential in square root of 2 log n log log. Okay, but this is heuristic. This is heuristic because we are somehow assuming that some of the density of the smooth numbers in the way we are constructing these numbers somehow behave the same way, like picking numbers at random from 1 through root n. I mean, these are not random numbers from 1 through root n. They happen to be specific residues of root n plus 1 mod n, root n plus 2 mod n, etc., etc. But we are going to say that, okay, as far as the smoothness degree concerned, this looks random enough. Okay, and we don't know how to prove this, but but this tells you how to reduce the 2 that we had in Dixon's algorithm to a root. Okay, and root 2 is still a number bigger than 1. We are not satisfied with this. We want to push it a little further down. Okay, and what we are going to do in the next class is to look at what is called the quadratic sieve algorithm due to Kalpomerans, which is a L half comma 1 algorithm where this 2 will be. Okay, and as you can imagine, the step that is going to be changed here is that we are basically saying that I have a set of numbers, which is this potential y1, y2, y3 all the way, and I only want to choose those numbers that happen to be B smooth. Can I do that step more efficiently? Okay, because so far there is no sieving operation that has happened. And we'll introduce the sieving operation. We'll revisit some more traditional sieves and get comfortable with how those algorithms work, and then try to apply it here. And it's a beautiful application on top of this to actually get rid of the square root. Okay, and that's going to be the focus of the next lecture. And yeah, and after that, I might just give a very high level exposition of what is called the number field sieve and stop with that. Okay, so this is all I wanted to do in today's this thing. So if there are any questions, we can go over it. Otherwise, we'll meet on Tuesday next. Okay, so great. So hopefully, I mean, there's some appreciation of the original Morrison-Brillhart approach and Dixon's algorithm. Dixon's algorithm is at least one provable randomized sub-exponential time algorithm for factoring integers, and but then we were like throwing in some heuristics in order to somehow shave off these constants little by little. Okay. So then let's just meet on Tuesday, and we'll see the quadratic sieve algorithm due to complex. Okay.